most terrifying ending of the universe might not be a massive explosion, not some final flash blazing across the sky, just the moment when nothing new ever happens again, and that moment stretches on forever. Look up at the night sky tonight. Stars burning. Galaxies spinning. Light that has travelled billions of years finally reaching your eyes right now. A universe that is loud, chaotic, bursting with motion, and all of it depends on something you cannot see, cannot touch. The way space itself is expanding, every second, in every direction at once. Stop for a moment and think about what that actually means. Galaxies are not flying through space like bullets. The space between them is stretching outward, like ink printed on a sheet of rubber being slowly pulled apart. The distance grows not because anything is moving away, but because the stage the entire universe performs on is getting bigger. The fate of the universe comes down to this. How will that stage behave going forward? If the expansion stays steady, the universe fades out in cold and silence, what scientists call heat death. If it accelerates beyond control, every bond from galaxies down to individual atoms gets torn apart, the Big Rip. And if it ever reverses, gravity pulls everything back into collapse, the Big Crunch. Three endings that look completely different, yet all of them trace back to the same unanswered question. What is space, really? And why is it expanding? To understand how the universe will die, you first need to accept something that human intuition struggles to grasp. The universe is not standing still, not in the sense that planets are orbiting or stars are drifting, something deeper and stranger than that. Space itself is stretching, continuously, everywhere at once. Picture two dots of ink drawn on a deflated balloon. When you blow it up, the dots move apart, not because they moved on their own, but because the surface between them expanded. Galaxies work the same way. The distance between them grows not because they are running from each other, but because the space between them is inflating. Meanwhile, gravity pulls in the opposite direction, holding planets around stars, stars inside galaxies, galaxies together in clusters. But at large enough scales, where gravity no longer has the reach to hold things in place, expansion wins, and structures begin drifting apart with nothing to stop them. In the late 1990s, observations of distant supernova explosions revealed that the universe is not just expanding but accelerating. The leading explanation is dark energy, a component that makes up roughly 68% of the entire universe, and which nobody fully understands. The real question is not that expansion is happening, it is how that expansion will change over time. If it stays stable, the universe grows steadily thinner, colder, less capable of producing anything new. If it intensifies beyond control, no force in the universe will be strong enough to hold anything together. And if it slows down or reverses, gravity could reclaim control and pull everything back inward. Three different outcomes that are really just three different answers to the same question: what will space do next? Of all the ways the universe could end, heat death is the least dramatic. The universe does not get destroyed in a single blow. It simply loses the ability to change, step by step, across spans of time that dwarf anything the human mind can picture. And the process begins with the deaths we can most easily imagine. About 5 billion years from now, the Sun will exhaust the hydrogen in its core. The nuclear fusion that has kept this star in balance for 10 billion years will no longer be strong enough to resist the gravity crushing inward. The core collapses, temperatures spike, and the outer layers begin to swell outward. The Sun becomes a red giant, large enough to swallow Earth's orbit entirely. Earth at that point, if it still exists, will be nothing like the world we know. The oceans will have boiled away billions of years earlier, the atmosphere stripped. Life as we understand it cannot survive those conditions. This is the first reminder in a long chain. Even the solar system, something that feels permanent and unchanging to us, is just a temporary structure in the cosmos. Around 6 to 7 billion years from now, the Sun will shed its outer layers into a glowing cloud of gas and leave behind a white dwarf, a core roughly the size of Earth but holding most of the Sun's remaining mass, radiating heat into space over billions of years with no nuclear reactions left inside, the light that once sustained life on Earth reduced to a faint, fading glow from a cooling remnant. But the Sun's death is not an exception. It is the fate of every star with similar mass, and there are hundreds of billions of stars like it in the Milky Way alone. Each one is counting down in its own way. While individual stars age and go dark, galaxies close enough to each other are still being pulled together by gravity. About 4 billion years from now, the Milky Way and Andromeda will begin to collide. Not like two cars slamming into each other, but a gravitational restructuring that plays out over billions of years, stars passing through each other because the distances between them are so vast, while the overall shapes of both galaxies warp and eventually merge into one. These collisions build larger structures, but they cannot hold back the expansion at cosmic scales. Only galaxies close enough to each other will still interact. The rest keep getting pushed further away, the gap between them and us widening faster than the speed of light until their light can never reach us again. But even those merged galaxies cannot escape a different kind of loss, quieter than anything before, yet far more complete. About 100 billion years from now, the distant galaxies will have drifted permanently beyond the reach of any observation, carried away by expansion faster than light, no signal from them able to reach us ever again. Every gravitationally bound group of galaxies becomes an isolated island in the dark. Think about what that means for a civilization born at that point in time. They look up and see only their own galaxy. Maybe a few neighbours still bound by gravity. No evidence that the universe ever held hundreds of billions of other galaxies. No way of knowing that the night sky was once thick with light from places billions of light years away. That is not just a loss of light, it is a loss of cosmic memory. Those of us alive today exist in a rare window, a time when the universe is still young enough for light from billions of distant galaxies to reach our telescopes. Over the following trillions of years, stars burn out one by one. Not in a night, not in a century, but one point of light at a time, disappearing from the sky across time scales so long that no living thing could notice the change within a single lifetime. What remains are cooling white dwarfs, neutron stars, black holes, and cold planets drifting through the dark. Galaxies are no longer glittering cities of stars, they become vast graveyards of stellar remnants. Around 100 trillion years from now, the era of ordinary star formation comes to a close. The gas and dust needed to build new stars has been exhausted or locked away in remnants that can no longer react. White dwarfs become among the last energy sources worth drawing from, and if any civilization survives to this point, they are no longer living under the light of young suns. They are clinging to the leftover warmth of dead stars cooling in the dark beneath a sky that will never see a true sunrise again. Further out still, rare events may spark new stars from collisions between white dwarfs or pockets of gas at galactic edges, but these are brief flickers, nowhere near enough to reverse the overall trend. The universe is not losing energy in any simple sense. It is losing the differences in energy that make life, motion, and new structures possible. Everything is drifting toward a state so flat and uniform that nothing interesting can happen anymore. And even that flat, uniform state is not the last stop. The universe keeps sinking deeper into darkness. White dwarfs, the brightest remnants left after the age of stars, begin to cool as well. With no nuclear reactions inside, they simply radiate away whatever heat remains, slowly, until they become cold. Dark objects physicists call black dwarfs. No light, no heat, drifting in complete darkness. But here is the more interesting question. Does the matter making up those dead stars actually last forever? Some theoretical models in physics predict that protons, one of the fundamental particles making up every atom, everything we can touch, may eventually decay on their own after enough time has passed. This is still a hypothesis, not confirmed by any experiment. But if protons do decay, then every planet, every stellar remnant, everything made of ordinary matter will gradually dissolve into subatomic particles and radiation over timescales that could stretch to numbers with millions of digits, so long that the current age of the universe would look like the blink of an eye by comparison. Whether protons decay or not, ordinary matter eventually stops playing any meaningful role. What remains are black holes, the last organized structures in the universe. They orbit each other, merge, grow larger, dominating a cosmos that is almost entirely empty. But even black holes are not permanent. In 1974, Stephen Hawking showed that black holes are not completely black. They leak a tiny amount of radiation outward through quantum effects at the event horizon. The process is extraordinarily slow. A supermassive black hole at the center of a galaxy could take roughly a Google years, that is 10 to the power of 100, to evaporate completely. That number is so large that ordinary language has no way of capturing what it actually feels like. When the last black hole is gone, the universe holds nothing but subatomic particles and radiation too spread out to interact in any meaningful way. No temperature differences large enough to do useful work, no structure complex enough to sustain motion or life. The universe reaches something close to thermodynamic equilibrium, an ending not from everything exploding, but from everything becoming too uniform, too thin, and too still for anything to ever happen again. But that only plays out if dark energy agrees to hold still, and nothing guarantees that it will. In heat death, dark energy acts like a constant, always present, always pushing space outward, but never growing stronger over time. The Big Rip starts from a different premise. If dark energy belongs to a class physicists call phantom energy, then its density does not stay fixed but actually increases as the universe expands. The bigger the universe gets, the stronger dark energy becomes, the faster expansion accelerates, a feedback loop with no off switch. The consequences do not arrive immediately. For billions of years, the Big Rip looks indistinguishable from heat, death, galaxies drifting apart, the sky growing darker. But once the expansion rate crosses a certain threshold, things begin changing in ways heat death never could. The largest structures in the universe are the first to break apart. Galaxy clusters, collections of thousands of galaxies once held together by gravity, lose their cohesion. Then individual galaxies. Stars get pulled away from each other. Galaxies lose their shape and dissolve into scattered streams of stars drifting through space. The night sky does not darken because stars have died. It darkens because stars have been pushed so far apart that their light can no longer reach anything. Then solar systems stop holding together. Gravity that once kept planets on their orbits is no longer strong enough to resist the accelerating expansion. Planets get pulled away from their stars. Viewed from Earth, the Sun would shrink on the horizon as the distance between them widens, not because Earth is moving away, but because the space between them is being stretched. Heat and light drop below what anything needs to survive. Atmospheres and climates collapse. As the Big Rip pushes down to smaller scales, it is not just orbits that fail. The physical bodies themselves cannot hold their shape. Solid matter gets stretched and broken apart. The things that once seemed most durable, rock, metal, planetary cores, stellar cores, all become fragile against the extreme expansion. Planets shatter piece by piece. Stars break apart from within. Everything that once had a defined shape loses it faster than any force can respond. Then comes the atomic scale. The electromagnetic force holding electrons around nuclei, the strong nuclear force holding protons and neutrons together, forces that seemed completely untouchable at the subatomic level also give way. Atoms are torn apart, nuclei broken open from the inside, and physical reality, in any sense any living thing has ever known, simply ceases to exist. The whole process follows an irreversible sequence. From galaxy clusters down to galaxies, from solar systems down to planets, from solid objects down to individual atoms, each layer of structure failing in turn, each failure arriving faster than the last, until there are no more layers left to lose. Unlike heat death, where the universe fades because energy runs out, the Big Rip ends the universe because space itself expands too aggressively for anything to stay connected. But there is still one possibility that points in the completely opposite direction. What if expansion does not keep accelerating forever, but one day weakens, stops, and turns around? The answer is this: expansion does not keep accelerating. It slows, halts, and reverses. Throughout cosmic history, everything has moved in one direction. Apart from each other, thinner, colder, the Big Crunch flips that direction entirely. For it to happen, gravity, or some shift in the nature of dark energy, would have to win out in the end. Given what current observations show about accelerating expansion, the Big Crunch is not the most favoured scenario, but it remains a meaningful, theoretical possibility, and in terms of sheer strangeness, no other ending of the universe produces quite the same feeling. The universe reverses its own history, the only one of the three endings that can do that. Distances that were growing start shrinking, galaxies get pulled back toward each other, and regions of space that were once cold and empty begin accumulating matter again. The feeling shifts. It is no longer loneliness, it is claustrophobia. The universe stops emptying out and starts crowding in. As galaxies draw closer, mergers happen at enormous scale. But it is worth being clear about what these collisions actually look like. They are not like two trains smashing into each other with debris flying everywhere. Individual stars rarely collide directly because the distances between them are immense. What happens instead is a gravitational restructuring on a cosmic scale, gas and dust compress together, high energy processes becoming increasingly violent, the overall shape of each galaxy warping and eventually folding into the other. As the universe keeps contracting, space that was once cold and dark begins heating up, the light growing denser with every passing billion years. Any hypothetical observer surviving to this stage would not see an empty sky. They would see a sky too full, too bright, too hot to look at directly. Every direction blazes because matter and radiation are being compressed from all sides at once. The universe approaches a state of extreme heat, density, and energy. Distinct structures like galaxies, stars, and planets lose all meaning, everything swept into a total convergence, from which nothing escapes. The Big Crunch is the complete opposite of heat death, not because everything is too spread out, but because everything is too concentrated. And it leaves open a question physicists have not definitively answered: is this an absolute ending? If the universe once began in a hot, dense state, the Big Bang, could a hot, dense ending be the seed of something new? Nobody can say for certain. But the question alone is enough to shake the way we think about time, about beginnings and endings. One thing has not changed after everything we have just been through. Humanity does not know which path the universe will take, and that mystery leads straight back to the most invisible thing in existence. Current observations show the universe is expanding at an accelerating rate. But the true nature of dark energy, the force believed to be driving that acceleration, remains poorly understood. If dark energy behaves like a stable cosmological constant, heat death is the most natural outcome. If it grows stronger over time and becomes phantom energy, the Big Rip becomes a real possibility within certain models. And if its nature changes in ways that allow gravity to eventually win, scenarios involving collapse remain theoretical questions that cannot yet be ruled out. Here is what makes this moment remarkable. We are living at a time when that question may actually begin to get answered. The European Euclid telescope and the American DESI instrument are mapping tens of millions of galaxies, measuring the expansion history of the universe with a precision never achieved before. Early results from DESI already hint that dark energy may not be constant at all, but evolving over time. If confirmed, that would rank among the most significant discoveries in the history of cosmology. When we observe distant galaxies, we are not just looking into the past, we are trying to measure the future of the entire universe. Heat death is the universe going dark in absolute silence. The Big Rip is the universe being dismantled layer by layer. The Big Crunch is the universe turning back on itself, collapsing, heating up, and possibly never truly ending. Each outcome is a different answer to the same question: what will space do next? Human lifetimes are far too short to witness any of these endings. But asking the question at all reminds us of something worth holding on to. We exist in a rare era, one that still has stars, still has light, still has the ability to observe and wonder. The universe may go cold, may be torn apart, may collapse back into itself, but the most frightening ending of all is perhaps none of those. It is the day we can no longer ask the question. Right now, the answer still lies in the most invisible and most powerful thing there is, the way space keeps expanding 1 second at a time, right now.